Okay, this is weekly challenge number 4 for the week of February 15th, 2021. This being challenge 4, it's quite a bit trickier than the previous couple of challenges, and so this this video is going to be very long, just like the previous, well, I guess all of the videos, because I tend to go into more detail than I probably need to. I will try to, the solution's actually right here for you. Except for this. You would need to remove that if you were to get this to work on Learn. But otherwise, you could go ahead and just pause the video, type this into Learn, and never have to hear from me again if you don't want to. But what I'm going to do this video is talk about this algorithm and make a tiny improvement. I'm not going to go into a whole bunch of improvements like I have done in the past, just because this algorithm, doesn't really deserve to be optimized, and I'll get into why that is in a minute. We're implementing a very classic sorting algorithm called bubble sort. And the idea here is that the main mechanism behind this, how a collection of numbers is sorted using bubble sort, kind of causes the largest numbers to sort of float to the top, if you will, and that's why it's called bubble sort. There are visualizations out there if you're the kind of person that likes visualizations. I am personally, and there are some good visualizations out there. We might actually link to that in the explanation section after you solve the challenge. But for now, the world is your oyster, or rather the internet. And I encourage you to go out and kind of read about bubble sort and try to understand the algorithm yourself first, because I'm not going to get super duper into the nitty gritty here. I probably am, because again, I'm long-winded and I can't help myself. But I still recommend trying to, kind of understand this algorithm first. But anyway, so it's a classical algorithms that is taught very early in computer science education, and there's a couple reasons for that. First, it's a very old algorithm. Second, it's very intuitive and easy to reason about. The concept behind bubble sort is very, very easy to reason about. It's relatively simple to implement. And there's kind of a lot to unpack. There's a lot to sort of talk about, especially if you're a computer scientist and you are studying something like algorithm analysis. And that's why this algorithm is so commonly seen in computer science education. But, we're not computer scientists, so I'm not going to get super into the nitty gritty here. Basically, even though I already have been talking for 3 minutes and haven't said really anything. Basically, bubble sort is a terrible algorithm. It's very, 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 very slow. Or rather, it does a bunch of work. You notice here, there's a nested for loop. There's 2 for loops sort of nested inside of each other. And the for loops are running out to the length of, or repeating, len nums number of times. So if nums has 10 elements, if it's a list of 10 numbers, then this outer for loop is going to run 10 times, and this inner for loop is going to run, 10 minus 1, or 9 times. And if you want a very kind of rough idea of how many iterations, essentially, your algorithm is going to take, and you have a nested for loop, you just multiply however many iterations the outer for loop is going to take times however many the inner for loop is going to take. So in this case, inner for loop is going to run 9 times, outer for loop is going to run 10 times, for a total of 90 iterations. Just for a list of 10 numbers, we're going to iterate 90 times. Which is horrible. It's a really bad algorithm, and that's why I said it doesn't deserve optimization. It's a great teaching tool, but it doesn't really need to. There's not much you can do. There's a saying, you can't really polish a turd, so hopefully I don't get in trouble for saying that and posting it on YouTube. Uh, I will say whoever invented this algorithm was very insightful, and if anything, it has served very well in teaching computer scientists the importance of optimization and approaching problems in certain ways. All right, so let's get into the algorithm itself. So we have this constant here, swaps, initialized to the value 0. This is not required by the algorithm. This is required by us for our challenge because we need to return a tuple with the first item representing the number of swaps required to sort the list. So this is just, yeah, again, not required by the algorithm bubble sort itself. This is a requirement for us for this challenge. Similarly for num iters, I have this in here just to count or to prove to you that this thing is going to run 90 times if I give it a list of 10 elements. And then it's also in there because I will make a small optimization and show you that we can cut that in half, that number in half. Okay, so result is copying nums. And the reason we're doing that is because you don't want to modify it's bad practice, essentially, in general, or maybe I should say as a rule of thumb, you should not modify the arguments of a function. So if you have some function and it accepts some object, like a list, any sort of mutable object, it's bad practice to modify that object. What you should do is make a copy and modify the copy and then return the copy. And then whatever the user wants to do after that is their choice. But we, as the programmer, don't want to modify our inputs, generally speaking. So that's why we're making a copy, and then we're going to sort of fiddle around and swap elements here and there in the result list. Okay. So this outer for loop, notice I'm using an underscore. And that's valid Python syntax. And that just means, that signifies to the reader that we are not using the iterator variable in this for loop. So yeah, that's just there to say, yeah, we're not using this the only thing we're using this for loop for, this outer loop, is to repeat some process. And that's going to run len nums number of times. And then the inner for loop, we're going to give the iterator variable the name index. And that's going to run len nums -1 number of times. And the reason for that is because we're essentially going to be comparing pairs of elements. So we're going to look at the index, or we're going to look at the value at the position index, and then the value at the position index +1. Okay, yeah, and this input statement is here for me for the purpose of this video so that I can actually just manually step through this algorithm and show you what's happening. Otherwise, it would happen too fast and it'd be hard to talk about. Okay, so the core logic here is if A is greater than B, sorry, I should say, so A is taking the value at the position index from result, and B is taking the adjacent item index +1, or the value at index +1. And then what we're going to do is say, well, if A is greater than B, we need to switch their place. So, and that's exactly what this is doing right here. We're just taking result at position index and giving it the value B, because we found essentially that B should come before A, right? We're sorting in ascending order. So that's what that's doing. And that's the core logic of, well, I guess I should say this is the core logic of the algorithm. And you'll see what's happening in a second here. Just a print statement just showing that we've swapped some elements if this happened to be true. And then we're incrementing the number of swaps, again, if this happened to be true. Otherwise, none of this code in this block here is going to run. That's fine. And then at the end of a single iteration, we're just going to increment num iters. Now, when this inner for loop completes the first time, or rather every time it completes, we're going to print this message, inner for loop completed, or inner loop completed, with some new lines, just to visually break up the data that we're about to print here, so I can just make it a little bit easier to visualize or see what's happening. And yeah, after the inner for loop completes, the outer for loop will sort of start over, and again, that's going to happen 10 times. And at the very end, we're going to finish sorting and then print the number of iterations that it took. All right, so I'm going to scroll up here and just show you that I have imported random. That is not necessary for this challenge or for the algorithm. That is for me to generate a random list of 10 randomly generated integers or digits, numbers between 0 and 9. And yeah, that's just for us to test the function. So I'm going to generate that. I'm going to print it just so we can see what it looks like at first, and then we're going to call on the bubble and sort it. All right, so I'm going to run the code here, and all right, so we generated this list right here. And on our first iteration, the index IDX is 0, and IDX plus 1 is 1, obviously. So we're checking the 0th and first values, which are 4 and 6. And notice 4 and 6 are already in order. They don't need to be swapped. And now we're checking 6 versus 5. So now we're checking these two elements. Those don't need to be swapped. Or I mean, excuse me, absolutely, they do need to be swapped. What I meant was 6 versus 6 does not need to be swapped. So yeah, the swap occurred and 5 and 6 switched places. Okay, and now 6 and 6 don't need to swap, so nothing's going to happen. And now 6 versus 8, that is also in order, so nothing needs to happen. And now we're looking at this pair right here, 8 and 6, so those need to swap. All right. And now we're looking at 8 versus 8. Nothing needs to happen. Now we're looking at 8 versus 3. We need to swap. Now we're looking at 8 versus 4. We need to swap. And 8 versus 8, nothing needs to happen, and we're going to complete our first inner loop. And now notice what happened here. So the largest item, or the max of this list, is 8. And we happen to have 3 of them in this list. But notice that at least one of them was put in its place. And we never need to look at this 8 ever again, because none of these other numbers are greater than it. So this is just there for the rest of the next 80 iterations that we have to do left. And don't worry, I'm not going to go that slow through the rest of them. I just wanted to go through this first one. But yeah, so that 8 is just going to sit there. And I'm kind of foreshadowing the optimization that we're going to make. All right, so we've started over back at the beginning of the list, and we're looking at 4 and 5. No swap needs to occur. 5 and 6, no swap, no swap, no swap, no swap. And now 8 versus 3. So we're all the way over here, and we're going to swap those. And then 8 versus 4, we're going to swap those. And now we're at 8 versus 8, no swap, 8 versus 8 again, right? That was this first 2. And then now we're looking at this second 2, and we've completed another inner loop. And now look at our list. All 3 of our 8s are sort of sorted. They never need to be looked at ever again. So they're in their place. And what I propose or predict is that one of these 6s is going to be right here at the end of this next sort of round, if you will. All right, so starting over, 4 versus 5, no swap. 5 versus 6, no swap. And now we're looking at this pair, 6 versus 3, swapping. Now we're looking at 6 versus 4, swapping. And voila. Look, that 6 is there. We know that 6 and 8 are not going to swap. So we're going to just move on to the next pair. 8 and 8 don't swap. 8 and 8 don't swap again. and that inner for loop is completed. So we're going to start over. And now I'm going to just kind of scroll through kind of more quickly, because hopefully by now you can see what's happening. All right. Should be one more. Yep. All right, I'm going to scroll back up. So I think this is where I stopped. Yeah, so we sorted that 6 and we were done. And then we jumped in, and then we, at the end of this loop, this inner loop, we sorted another 6 and put it in its place. At the end of the next loop, we're going to put another 6 in its place. So all of these elements never need to be looked at ever again. And look, we're performing all of those checks anyway, which we know we don't need to do. So again, that kind of foreshadowing the optimization that we're going to make, or one of them. Okay, yeah, and then I guess another thing to note is that, we started out doing kind of a lot of swaps, and as we go, as this outer for loop kind of keeps repeating, notice we're doing fewer and fewer swaps up until a point where we're already swapped, or sorted. No swaps occurred at all during this iteration, or this iteration, or this iteration. That was 30 operations, or 30 iterations, each with a Boolean operation that didn't need to take place because we were already sorted. So hopefully now you can sort of kind of are starting to understand why this is just a very, very, very slow, poor performing algorithm, because it's doing so much more work than it needs to do. All right, yeah, and then so finished sorting, number of iterations was 90, and the number of sorts required, or swaps required, to sort this list was 15. Right. So what we're going to do in order to make our slight optimization, again, I'm not going to go into a whole bunch of different ways to optimize this, again, because I don't think it deserves it. Being a little cruel, this is still a very cool algorithm. It's very easy to reason about, again. Yeah, anyway. So what we're going to do is, instead of calculating nums, length of nums twice, and I mean, we could have done this at the beginning, just because, we are calculating it twice, and that's kind of unnecessary. But that's not the optimization I'm talking about. I'm talking about, let's see, after this inner for loop completes, remember, let me scroll up here. At the end of that iteration, we put another one of the largest numbers in its place, and we never needed to look at it again. So we can essentially ignore this last 8 and just look at the rest of these. So what I'm going to do is subtract 1 from n, and then this inner for loop, its length is going to change. So it's going to start at 9 for if nums is 10 elements. It'll start at 9, this inner for loop. It'll complete that iteration, and then we're going to subtract 1 from n, and this inner for loop is then going to go all the way out to 8 instead. And then, each time we complete an iteration, we're going to decrease the value of n by 1. Because remember, each iteration, we're putting another one of the largest numbers of the list in its place. And you can see that here, that 6 got sorted, and then we never needed to look at the rest of those elements ever again. And then we put another 6 in its place. And then we can just ignore all of those. And then we just have to sort this much smaller list. Okay, so that's the optimization that I'm talking about. There are other small optimizations you can make, but I'm not going to get into them, but I'll just show you. You know what? I'm going to, oh, right. I forgot. I basically wrote a clean version of the bubble sort. And well, we'll get to that in a second. I forgot that I do still need to run this because I want to show you that we've cut our number of iterations that we need to perform significantly. So I'm just going to spam the enter button to just make this thing sort and complete. And okay, so on the first round, we did, so checking. You can see that we did that 10 times. Inner loop completed, and then so we decrease 1 from n, or we decrement n, and then we're doing 1, 2, 3, 4, 5, 6, 7, 8 checks. I may have miscounted that. It might be start with 9, whatever. The point is that we've decreased the number of checks that we did, and then we've decreased it again, and we decrease it again, decrease it again, decrease it again. And notice we're still doing quite a bit of extra work here that wasn't necessary. And so that's what I was talking about. There are more optimizations you can make. We can say, okay, if we went through an entire inner loop without making any swaps, we're done. We don't need to do any of this other work ever again. But yeah, I'll leave that as sort of an exercise for you to see how you can implement that extra optimization. What I wanted to get to is that we cut our iterations in half to 45 instead of 90. So it's still pretty bad, but it's not as bad as 90. And then, yeah, it would be the same number. I guess I'll prove that the number of swaps is constant. So we still do the same number of swaps. And then I need to comment this out because that was our little optimization key. Okay, so I'm just going to sort this list multiple times. I'm going to get rid of that so I don't have to manually go through. And get rid of that. I'll just show you the output. Okay, so we took this list, we sorted it in 90 iterations because I took out this optimization right here. And did 19 swaps. And now if I put that optimization back in and run it again, we can see we still do 19 swaps, but we just cut the iterations in half. All right. Yeah, and then I did have a sort of clean version of the algorithm without sort of the extra constraints that we put where you have to track the number of swaps, and then without all of my print statements and stuff. So this is the algorithm itself, just clean bubble. So I called it clean bubble. So yeah, sort of like a pure representation of the actual core mechanism behind bubble sort. And it should be said that there are actually a couple of different ways to implement this. But wow, we're at 23 minutes. So yeah, I'm just going to end the video here. Again, see if you can, as an exercise, figure out a way to, instead of doing all of this extra work right here, we already noticed, or we already had our list in sorted order after this last iteration right here. And we didn't need to do any more of this work. Actually, that's a little misleading. We did need to do this at least. But after this, no swaps occurred, so we could have just left it from there, and we didn't have to do any of these other checks here. Yeah, so again, leave that to you as an extra little challenge for yourself. All right, we will see you next week.